In Bose-Einstein statistics, today we are going to discuss a very important problem, and this is actually about the Bose-Einstein condensation, or you may also say Bose-Einstein condensate. Actually, this is a very important phenomenon, and this can be explained on the basis of Bose-Einstein statistics. As you know that the particles or group of particles which obey the Bose-Einstein statistics are called bosons, and bosons do not obey Pauli's exclusion principle. In fact, bosons favor grouping. When you say that bosons favor grouping, what does it mean? It means, let us say that there are a large number of bosons in an enclosure. Let us say these are the different bosons, and these are different energy levels or quantum states in which these bosons can be distributed. If there is a boson in any quantum state previously, then if these bosons have to remain or distributed in this quantum state, then the boson will like to occupy the quantum state which has already occupied by some bosons. So we say that the bosons actually obey or favor grouping. Okay. So I have mentioned here that you can see that if there is a boson in a particular quantum state, the probability of another boson joining it increases. Okay. In fact, more the number of bosons in a quantum state, larger is the probability of another boson joining them. Okay. Actually, this property of boson is responsible for Bose-Einstein condensation. We will explain this fact in very detail theoretically, but before that we will see that when this Bose-Einstein condensation will take place in a qualitative way, and then we will see the same thing in a quantitative manner. As you know, already I have discussed in the previous lecture in classical statistics that if you consider any system, let us say a gaseous system, then each atom of that system is associated with de-Broglie wavelength lambda. Okay. And this de-Broglie wavelength lambda is actually dependent on the temperature. When you find the thermal de-Broglie wavelength associated with any particle of mass m, that thermal de-Broglie wavelength is given by lambda equal to h over a square root of 2 pi mkt, where you know that this k is Boltzmann constant, m is mass of that particle, and T is the temperature. So you can see that this wavelength, which is called de-Broglie wavelength associated with the particle, depends on temperature. Actually, this lambda is inversely proportional to a square root of the temperature T. So if you are talking about room temperature, then the value of lambda is such that it is almost 10 to the power 4 times less than the interatomic distance. If you consider that these are the two atoms of a system, let us say this is atom number 1 and this is atom number 2, and at room temperature D is the separation between these two atoms, and at the same time, at the same temperature, you consider that lambda is the de-Broglie wavelength associated with that atom. Okay. Then it is seen that this lambda is almost equal to D divided by 10 to the power 4. So you can also say that in this condition this lambda is much smaller than D. It means the interatomic separation is much larger than the de-Broglie wavelength or the thermal de-Broglie wavelength associated with the atom at room temperature. So you can think that in this condition the wave packets of the two atoms will not get overlapped, and so the atoms will have actually individual identity, and the atoms will be not indistinguishable, but they will be distinguishable. And as in this condition the atoms are distinguishable, so the physics behind that system will be dealt in terms of the Maxwell-Boltzmann statistics, not Bose-Einstein statistics or quantum statistics. Okay? So even at room temperature, the atoms of that gas do not obey the quantum statistics, because the atoms will be indistinguishable, since the wavelength associated with the atoms will be much smaller than the interatomic separation, and so there will be a little chance of overlapping of wave packets, and the atoms will have individual identity, and so they are distinguishable. But think what will happen when we actually lower the temperature of the system. As you can see this result, that wavelength lambda is inversely proportional to a square root of t. Okay? So with decrease in T, lambda will increase. When temperature will be decreased, lambda will increase, and at extremely low temperature, this lambda will have such a value that this lambda will become just comparable to the interatomic separation, or even you can say that this lambda will be greater than d. It means in this condition the wave packets of the atoms will get overlapped at ultra low temperature. Let us say when temperature just tends to 0 Kelvin, the lambda will have such a larger value that it will be greater than the interatomic separation, and the wave packets of the atom will get overlapped. And when the wave packets of the atoms will get overlapped, you can think that the atoms will lose their individual identity. Okay? And they will just behave like a superatom governed by the same wave function. So, and that's why it is you can think that at ultra low temperature all the atoms move on to the lowest energy state. All the atoms. So all the atoms will be in the same energy state or in same quantum state, and that is actually the ground state of the system. So at ultra low temperature all atoms are found in this ground state, and this phenomenon is actually called Bose-Einstein condensation. That is the presence or the existence of all the atoms of the system in a particular quantum state, which is actually the ground state or a state of lowest energy, or you can say zero energy. This phenomenon is called Bose-Einstein condensation, and we simply say that Bose-Einstein condensate has been formed. Okay? So I think you have understand that this Bose-Einstein condensation will take place at ultra low temperature, when actually the temperature will tend to 0 Kelvin. Only then this phenomenon will take place. And what actually happens during this phenomenon? Actually all the particles, all the bosons of our system go to the same quantum state, in a single quantum state, and that phenomenon is called Bose-Einstein condensation. Okay? Actually, we can say that this Bose-Einstein condensation, which I have written in brief BEC, corresponds to a transition from a set of disordered atoms to a coherent matter waves. Okay? atoms were actually disordered at the higher temperature. But when the temperature is very low, then the atoms actually get completely ordered. They are almost in same quantum state, and so you can say that there is a transition of disordered atoms to a coherent matter waves. Just like in case of laser, you know that an ordinary light is transformed into a laser light of a strictly monochromatic laser light. Okay. So I think you have definitely understand that what happens during the Bose-Einstein condensation. Now actually we will explain this macroscopic phenomenon of Bose-Einstein condensation theoretically. Okay, and for this we consider there is an assembly of n bosons, as you have learnt earlier. And among these n bosons, let us consider that there are n1 bosons in energy state E1, and that energy state is G1 fold degenerate. There are n1 bosons in energy level or energy state E1, and this energy is G1 fold degenerate. It means in this energy level there are G1 quantum states. Okay. Similarly, there are n2 atoms present in the energy level E2, and this energy eigenvalue is G2 fold degenerate. And in the same manner you can say that there in general there are nn atoms or bosons in quantum state with energy En, and its degeneracy is Gn. Okay. Now, as this assembly follows the Bose-Einstein statistics, so you have learnt in the previous lecture what will be the number of bosons in ith energy level. You have definitely learned. Actually, this is also known as Bose-Einstein distribution law. And you know that in Bose-Einstein distribution law, we define the occupation probability F of EI, which is actually Ni divided by Gi, which is average number of bosons per quantum state, and that is 1 over e to the power minus alpha, e to the power minus beta EI, and minus 1. Okay. So you can see that Ni can be written as Gi over e to the power minus alpha into e to the power minus beta EI minus 1. Okay. Now, to understand the concept of this Bose-Einstein condensation, let us consider two quantum states. The first quantum state or the lowest quantum state, which is of zero energy, this is called actually the ground state. Okay, and we consider another state, quantum state, which is in which the energy is greater than zero, that is not zero, and this is actually called the excited state. Okay, excited state. As I have told you that when all the bosons will be in ground state, that phenomenon will be called Bose-Einstein condensation. So we will learn that when all the bosons will be in this ground state. And for this, let us consider in general that this N0 is the number of particles, or you can say bosons, in the ground state which has energy 0. This is the number of particles in ground state. And we also assume that this Ne is the number of particles or bosons in excited state, that is in a state where energy is not equal to 0. Now, you can see that this Ni represents the number of particles in an energy level having energy EI, which is not zero. So actually this Ne, which represents the total number of bosons or total number of particles in excited state, can be found simply by summing up the value of this Ni. Okay. Now, as the total number of particles is n, and you have assumed that n0 is the number of particles in ground state and Ne is the number of particles in excited state. So this total number n will be equal to n0 plus Ne, and therefore you can see that this Ne is equal to n minus n0. Okay, so Ne, which is equal to n minus n0, that is given by summation over I Ni, and as according to equation 1 you know the value of Ni, so this will be summation over I Gi over e to the power minus alpha times e to the power Ei divided by kT minus 1. Okay. Now we will have to find what will be actually the number of quantum states or the number of phase cells, you can also say, in a particular energy range between E and E plus D. Okay, E and E plus D. And for that, first of all, you will have to know what are actually the number of quantum states in the momentum range between P and P plus dP. And this thing you have actually studied several times. So I have written it here directly. The number of quantum states lying between momentum P and P plus dP, this is also called density of states, and you know this density of states is given by what? This is 4 pi V P square dP divided by h cube. When you do not take the spin of the particle under account, but if you consider the spin of particle under account, then you will have to multiply this by the spin degeneracy, or you can also say spin multiplicity. As in the problem of black body radiation, we have seen that the photon has there two states of polarization or two spin states. So you have actually multiplied this result 4 pi V P square dP by h cube by the factor 2. So in general, if our particle has a spin quantum number s, then its spin degeneracy, or you can say the number of spin states, which is denoted by this symbol Gs, is equal to 2s plus 1. 2s plus 1. For example, if s is 0, particle is spinless, then what will be Gs? Gs will be equal to 1. Okay? But if s is equal to, let us say, 1, then Gs will be equal to 3. Okay? So actually the density of states will be what? That will be equal to Gs times 4 pi V by h cube P square dP. Although for a spinless particle, this Gs has value 1. Okay? So if you will consider that in our present discussion the particle is spinless, then this Gs will be 1. But if it is not spinless, then you have to write Gs, which means 2s plus 1. So for getting the general result, here I am not taking Gs equal to 1, but I take that spin degeneracy is Gs. Okay? So you can see from this result, as the momentum or energy has actually continuous distribution, so to get the number of particles in the excited state, this summation will be changed into integration. Okay? And in terms of momentum, what will be the value of this Ne? You can see that this will be integral 0 to infinity G of P dP divided by e to the power minus alpha times e to the power E by kT. But as you know, thus this E is equal to P square over 2m. So here at the place of E I have written E as P square by 2m. Okay. Now when you will substitute the value of this G of P dP from this equation 3, you can see your result will be Ne equal to 4 pi gs v divided by h cube integral 0 to infinity P square dP divided by e to the power minus alpha times e to the power P square over 2m kt minus 1. See this result. Okay. Now this the product of these two exponential terms, e to the power minus alpha into e to the power P square by 2m, you know that power can be added, will be added. So this is e to the power minus alpha plus P square by 2m kt. Okay. So this is the value of in fact Ne. Okay. Now to evaluate this integral, we actually use the technique of substitution method. So for evaluating that integral, let us consider that this P square by 2m kt is equal to x. We consider. Okay. So you can see this when you will take differential of this x, this will be dx equal to, and differential of P square will be 2p dP. Okay. Divided by 2m kt. Now this 2 and this 2 will cancel out, so this is P dP over m kt. And so from here you can see that this dP will be equal to m kt divided by P, you can see dx. Okay. Now making this substitution, that at the place of this P square by 2m kt, we will write x, and instead of dP, now we will write m kt by P dx. Okay. So make this substitution in this equation, you can see in this equation number 4. So the outside factor, that is 4 pi gs v divided by h cube, this will remain at its. Instead of P square, you can write from here that P square will be equal to what? So you can see P square is 2m kt times x. So you can see I have written here that this is 2m kt x. Okay. P square. And there is dP here, you can see. There is dP. And see this result. dP, this is equal to this much. You can see. dP is this much. See this. M kt by P. So I have written here m kt dx divided by P. But you can see that P will be simply equal to root over 2m ktx. So here in denominator I have written root over 2m kt and x to the power half. This is actually instead of a square root, power half. Okay. And the other factor which remains is what? This is 1 over e to the power minus alpha plus P square by 2m kt minus 1. Now again we will write x instead of this P square by 2m kt. We will write it. So you can see this is the remaining factor. This is 1 over e to the power minus alpha plus x minus 1. Okay. Now we will simplify it. You can see that this 2m kt in square root of 2m kt in denominator will cancel out, and here there will be actually 2m kt square root, and here is m kt. So actually on m kt there will be 3 by 2 power. Okay. And there will be root 2, 4 root 2. So this result can be written in a suitable form like this. This is gs times v. Here I have written gs or not? Yes. So you can see gs times 2 pi m kt to the power 3 by 2 times 2 by root pi integral 0 to infinity x to the power half e to the power minus alpha plus x minus 1 dx. Okay. Actually, you can see here. Actually, here is only 1 pi, but you have written pi to the power 3 by 2. So there is an extra square root of pi. So I have divided it by this much. Again, the numerical factor is actually 4 root 2, and here we have written 2 to the power 3 by 2. Okay, so one factor remains here 2. Actually, this 2 by root pi has been written separately by multiplying to this integral for convenience. You will see later that when you will take this 2 by root pi as a multiplicative factor of this integral, your result will be very simpler. So that this has been taken as a multiplicative factor. Okay. Now, this factor inside this square bracket, let us consider, is equal to f of alpha. So f of alpha is equal to 2 over root pi integral 0 to infinity x to the power half divided by 1 over a e to the power x minus 1 dx. Actually here, this 1 by a has been written at the place of e to the power minus alpha. E to the power minus. Actually, e to the power alpha is written as a. Okay. So e to the power minus alpha can be written as 1 by a. Okay. Okay. So you can write now this value of Ne. This is Gs V over h cube times 2 pi mkt to the power 3 by 2. And as you have assumed this factor equal to f alpha, so I have written here f alpha instead of that factor. Okay. Now, this function f of alpha can be easily evaluated when you will take that this a is less than 1. In fact, by making the binomial expansion, you can evaluate the value of f of alpha when you assume that a is less than 1. So let us see. In denominator, there is in this equation 6 1 by 1 over a e to the power x minus 1. When you will take this term in denominator, in numerator, the power will be minus 1, and by binomial expansion we can evaluate it. So you can see the factor was in denominator 1 by a e to the power x minus 1. This was the factor in denominator. So when you will take it in numerator, the power will be minus 1. Now take this first term 1 by a e to the power x as a common factor. Since there is a power of minus 1 as a whole, so when you will take it outside, then this will be a into e to the power minus x. Are you getting the things or not? Okay. Definitely this is a simple algebra. And in second term there is 1. So we will have to divide this 1 by a e to the power x. So 1 by a ex, this will be a into e to the power minus x to the power minus 1. Now this result can be actually expanded by binomial expansion. In fact, 1 minus x to the power minus 1, this is 1 plus x square plus x cube and plus so on. Okay. Here at the place of x there is a e to the power minus x. Okay. So you can write this is a e to the power minus x, 1 plus a e to the power minus x plus a square e to the power minus 2x plus a cube e to the power minus 3x and so on. Okay. So in this condition, what will be the value of alpha? You can see the alpha is given in this equation number 6, and this is 2 over root pi integral of x to the power half divided by this factor dx. And you have evaluated this factor 1 by a ex to the ex minus 1. So substituting this value in this equation 6, you can write that f of alpha equal to 2 over root pi. Sorry, the page has been turned because this is a long lecture and my iPad regularly obstructed. You can see this will be 0 to infinity a e to the power minus x x to the power half. Okay, and 1 plus a e to the power minus x plus a square e to the power minus 2x and so on. Okay, actually this value has been substituted here. Now operate this integral separately on all terms. So you can see this is 2 over root pi and a 0 to integral 0 to infinity e to the power minus x times x to the power half dx. Now this outside factor will be multiplied by this, there will be a square, so a square is outside, and e to the power minus x into e to the power minus x, this will be e to the power minus 2x times x to the power half dx and so on. Okay. Now from the concept of gamma function, you know that the value of this standard integral 0 to infinity e to the power x times x to the power half dx, this is root over pi by 2. You can see this integral by the concept of gamma function. Okay. Now the second integral will be what? A square is at is actually e to the power minus 2x into x to the power half dx. When it is evaluated by the concept of gamma function, then it is found that this is root over pi by 2 times 1 by 2 to the power 3 by 2. Okay. And similarly, if you will write the third term containing a3, and this is integral 0 to infinity e to the power minus 3x x to the power half dx, then its integral will be what? This will be root over pi by 2 times 1 by 3 to the power 3 by 2. Okay, 3 to the power 3 by 2. So you can see that we can take this a into root pi by 2 as a common factor, and the value of f of alpha can be written as 2 by root pi times root pi by 2 into a into 1 plus a by 2 to the power 3 by 2 plus a square by 3 to the power 3 by 2 and so on. Okay. Now you can see that this root pi and this root pi, this 2 and this 2 will cancel out and multiply by this a to the terms inside the bracket. So this will be f of alpha equal to a plus a square by 2 to the power 3 by 2 plus a cube by 3 to the power 3 by 2. So this is the value of f of alpha in terms of a, where a we know is equal to e to the power alpha. Okay. Now if you consider that this a is much smaller than 1, then you know when a will be much smaller than 1, the higher power value of a, that is a square, a cube, a4 and so on, these will be negligibly small. Okay. And as they are negligibly small, so we can neglect all the terms containing the higher powers of A. So f of alpha in that condition can be simply written as f of alpha equal to A. But this will happen when A is much smaller than 1. Now, as you know, in case of a Bose gas, the chemical potential is always negative. It means chemical potential of Bose gas is always negative. And as you know that A is equal to what? This is e to the power alpha, and you know that alpha is mu divided by kT. Okay? But mu is negative. So actually, although here there is not minus sign, but when you will put the actual value of chemical potential mu, there will be a negative sign there. So in that condition, since E exponential has negative power, so its value will be definitely less or equal to 1. Okay? And when the temperature T will be lowered, mu by kT will decrease, but as there is minus sign, so you can say that will increase. Okay? So, lowering the temperature A will increase from 0 to a maximum value which is equal to 1. Since A is never greater than 1, its highest value is 1. So when temperature is lowered, then the value of A starts increasing and reaches to the value of 1, which is its maximum value, when temperature will actually approach to the 0 Kelvin, extremely low temperature. Okay? So you can see that A is equal to 1. That is, A becomes maximum at a particular temperature. The temperature at which this A is maximum, that is called critical temperature, and we denote that very temperature by the symbol Tc. So you can say that at critical temperature Tc, A is equal to 1. Okay? Now, how we can find the value of this Tc? You can see, if your aim is to find the critical temperature Tc, and this is definitely we have to find to deal with the Bose-Einstein condensation. So to find the value of Tc, we definitely have to put A equal to 1. So using A equal to 1 in this equation, in the equation in which equation? In the equation number 7. See equation number 7. This is your equation 7. Yes. When we will put the value of F alpha and take A equal to 1, then as A is equal to 1 only when T is equal to Tc. So you have to put here T equal to Tc. And actually in this condition, this Ne, which is the number of particles or bosons in excited state. So actually at this critical temperature or a temperature above the critical temperature, we can assume that almost all particles are in excited state. There is no particle in ground state. So this Ne will be almost equal to N. So making these substitutions in that equation 7, you can see that Ne is almost equal to N, and Ne was what? That was Gs into V 2 pi m kT divided by h square to the power 3 by 2. Actually there was h cube in denominator, but when you will take h square to the power 3 by 2, the result will be h cube. So instead of h cube, it has been written that h square to the power 3 by 2. And instead of T, now we write Fc, or now we write Tc. Okay? I have not substituted the value of f of alpha directly, but I have written f of alpha for your convenience. See the expression. Okay. Now we will substitute the value of this f of alpha. Other factors remain same. F of alpha, you have seen this is a plus a square by 2 to the power 3 by 2 plus a cube by 3 to the power 3 by 2. Okay. But as we can see here, that when T is equal to Tc, that is temperature of the system is equal to the critical temperature, then this A is also called fugitivity, and this fugitivity A is actually equal to 1, which is its highest value. So let us now substitute 1 for A. So the series in this square bracket will be what? This will be 1 plus 1 over 2 to the power 3 by 2 plus 1 over 3 to the power 3 by 2 and so on. Okay. Actually, this series defined in this square bracket is written as zeta 3 by 2. This symbol is zeta. Actually, this is Riemann function. Riemann function in general is denoted by the symbol zeta of L, where L is any number which is raised on this. You can also say that 1 by 1 to the power 3 by 2. Okay, and 1 by 2 to the power 3 by 2. 1 by 3 to the power 3 by 2. Similarly, the next term will be 1 by 4 to the power 3 by 2. So this series is written as zeta 3 by 2, which is actually a Riemann zeta function, and actually the value of this zeta 3 by 2 is equal to 2.612. This is its value. Okay. So you can write the total number of bosons or particles is equal to Gs times V 2 pi m KTC over over h square to the power 3 by 2 times zeta 3 by 2. And from here you can easily find what will be this Tc. So making the simple algebra, you can write this Tc is equal to this much. You can write it. This is n over zeta 3 by 2 Gs into V whole to the power 2 by 3 into h square by 2 pi mk. This is the expression for this Tc. Okay, and this yes, and as I have told you that this zeta 3 by 2 is equal to 2.612, and in general this zeta L is called Riemann zeta function. Okay. In fact, it is seen from experiment that for all Bose gases, this critical temperature is very small, very small. In fact, when you will find the value of critical temperature for 2He4, this is, you can say alpha particle or helium-4, which is a boson. For this, the critical temperature is 3.13 Kelvin. Okay, 3.13 Kelvin. So this is actually a very small temperature because it is in Kelvin. Okay, and now we can find the condition for Bose-Einstein condensation in terms of this critical temperature. Actually, we will have to consider the condition that the temperature of our bosonic system is less than Tc. That is, we will discuss the result when T is smaller than Tc. Okay. Actually, when T is less than Tc, you know the chemical potential of Bose gas mu is equal to 0. And when mu will be 0, what will be this alpha? Alpha will be 0, because you know that alpha is equal to mu by kT. And since mu is 0, so this will be 0 divided by kT, and this is equal to 0. Okay. And in this condition, what will be A? As you know that A is equal to e to the power alpha, but alpha is 0, so this will be e to the power 0, and that is equal to 1. Okay. So when you consider that the temperature of the Bose gas is less than critical temperature, in fact in that condition, you know, the constant A will be equal to 1. So in this condition, the number of particles in the excited state will be what? As you know, that number of particles in excited state is equal to n minus n naught, and that will be equal to 2 pi m kt to the power h square whole to the power 3 by 2 gs times v times zeta 3 by 2. Okay. And you can see that actually since n minus n naught is equal to this much, so you can say that n will be greater than this value, that is 2 pi m kt over h square to the power 3 by 2 gsv zeta 3 by 2. Okay. So you can say that the excited state will receive as many particles as they can hold according to this equation 11. Okay. And the remaining number of particles, that is the particles which are not in excited state, those will remain in the ground state. Now see this result, Ne, you can see Ne is proportional to T to the power 3 by 2. Ne is proportional to T to the power 3 by 2. And when you have defined this N, see this result, N is proportional to Tc to the power 3 by 2. Okay. N is actually the total number of particles, and Ne is the number of particles in excited state. So as you can see, Ne is proportional to T to the power 3 by 2, and N is proportional to Tc to the power 3 by 2. So you can write that Ne over N, this is equal to T over Tc to the power 3 by 2. And therefore, Ne is equal to N times T by Tc to the power 3 by 2. And therefore, the number of particles in ground state will be what? As N0, you know this is N minus Ne. Now, substitute the value of Ne from this equation 12. You will get N0 equal to N times 1 minus T by Tc to the power 3 by 2. Okay. So you can see that number of particles in ground state depends on the temperature of our system T. As if it is clear from this result that as T is decreasing, T is lowered, T decreases, what will happen? When T will decrease, you can see that T over Tc will become more and more smaller. And when it will be more and more smaller and you have to subtract it from 1, so you will get larger and larger. It means on decreasing temperature, the number of particles N0 in the ground state increases. Ground state increases. And you can see if this T tends to 0 Kelvin, T tends to 0 Kelvin, what will happen? When T equal to 0, you can see that this N0 will tend to N, where N is the total number of particles and N0 is number of particles in ground state. So you can say that in the limiting case, when T tends to 0 Kelvin, then all particles, all bosons are in the ground state, in the same quantum state, and that quantum state is the state of lowest energy, that is of 0 energy. Okay. And that is actually the situation when Bose-Einstein condensation takes place. So you can easily see that the all particles will remain in ground state when T tends to 0 Kelvin, and this famous phenomenon is known as Bose-Einstein condensation. Okay. So I hope you have definitely understand that temperature is the most important factor which is responsible for the Bose-Einstein condensation. For it, we need the ultra low temperature and the bosonic system. Okay. Actually, in classical physics, we also talk about the condensation of vapor condensation. Okay. But this vapor condensation and Bose-Einstein condensation both are entirely different things. Actually, vapor condensation takes place by decreasing the temperature of vapor, and that is actually condensed into liquid, and that phenomenon actually takes place in general physical or geometrical space. But this Bose-Einstein condensation is purely of quantum mechanical origin. In this case, ordinarily our gas is not converted into any liquid, but all the atoms of the gas come into the same quantum state, which is actually the quantum state of lowest energy. Actually, this Bose-Einstein condensate possesses many peculiar, many unusual properties. And some of the unusual properties of Bose-Einstein condensate we will also discuss in the forthcoming lecture. For example, the liquid helium will be discussed, and you will see that this liquid helium shows so many peculiar properties. Okay? And can you think that why this Bose-Einstein condensate possesses many unusual properties? The reason is that as all the particles are in the same quantum state, so all particles now behaves just like a single particle or single atom, which is called superparticle or super atom, and they are all governed by the same wave function. And that's why you can say that the Bose-Einstein condensate has so many peculiar properties. So I think that you have clearly understand what is this Bose-Einstein condensation. And in the next lecture we will see the liquid helium properly as an application of Bose-Einstein statistics.